Good morning. This is Greg Troutwine, editor and associate publisher, offshore engineer, and I welcome you to the webinar, Offshore Wind, North American Opportunities and Challenges. We have a great lineup of 3 speakers today, including Philip Lewis, the Director of Research, World Energy Reports, Fred Zaukman, the Head of Market Development and Government Affairs, Orsted Energy, and Matthew Tremblay, Senior Vice President of Global Offshore Markets with ABS. Just as a format, each speaker will be given a 12 to 15-minute presentation with insights on the current progress, the future pace, and the direction and development in the growing offshore wind market in North America. Following the presentations, we will have an approximate 15-minute Q&A with questions from the audience. So please use the message board on this platform to ask questions anytime during the presentations, but all questions will be reserved for the last 15 minutes. To start, I'd like to welcome Philip Lewis, the Director of Research at World Energy Reports. Phil has more than 30 years of corporate and commercial management and strategic planning experience across the shipping, heavy engineering, and offshore energy spaces. And this year, he authored the report, The Outlook for Offshore Wind Power, the Frontier of Future Energy. Welcome, Phil.
Thanks, Greg. Morning, ladies and gentlemen. So let me start by introducing who we are. World Energy Reports is part of International Maritime Associates, a business consulting firm formed in 1973 to provide market analysis, strategic planning, business development, and project implementation support to clients in the energy, marine, and industrial sectors. Over the past 5 decades, IMA has performed more than 350 business consulting assignments for over 170 clients in 40+ countries. WAR Products produces multi-client studies in rapidly growing market sectors where there are wide industry requirements for up-to-date objective market information for business planning and benchmarking. Current WER studies focus on offshore wind market, floating oil and gas production, and offshore gas liquefaction. And we have developed and maintained proprietary online databases and mapping services in each of these sectors. Next, please, Mark. So why are we interested in wind? It's a strong growth from a small base, an unlimited resource, and huge potential project activity. Next, please. So offshore wind, as we said, is growing rapidly from a low base with significant regional variations in market penetration. We reached around 25 gigawatts of installed capacity at the end of 2019. And by the end of 2022, we're looking to achieve 56 gigawatts, driven by Europe and Asia Pacific, and mainly China with the new builds. Next, please. Europe, Asia, and North America lead the way to around 205 gigawatts of installed capacity by 2030, calling for around $390 billion of investment. Again, driven by Europe, mainly the UK, Asia, China, driving there. And then we'll see the US become a top 3 player by the end of the decade. Next, please. As the industry matures in key markets, CapEx and OpEx costs are falling, making wind more competitive. Offshore wind LCOE is reducing, witnessed by historic and current auction prices, and puts offshore wind in a competitive band with fossil fuels in European and Chinese markets, and is set to reduce around 10% each time installed capacity doubles. Wind farm CapEx is around $3,000 per kilowatt with transmission, or around $2,000 per kilowatt excluding transmission, obviously regional variations and project variations. Lifetime recurring OpEx provides significant opportunity for the OEM and logistics support supply chains. As we see from the pie chart on the right, OEM forms a major part of lifetime spend on an offshore wind farm, and turbines the largest single CapEx item. Next, please. So let's have a look at some of the technical developments in offshore wind, from foundations accommodating deeper water projects, turbines and installation vessels getting bigger, transmission substations getting bigger, and wind becoming a key element of supporting hydrogen in energy transition. Next, please. So different foundation solutions are seen as turbines go deeper and further offshore, from monopiles and jackets, tripods, currently seen to be in a 50 to 60 meter maximum water depth, in the future probably going up to 70, 80 meters, with floating offshore solutions from 30 meters, but really cost competitive over 60 meters, and that's TLP, semi-subs and spars. Next, please. Monofile fabrication is centered in North Europe and China. And for the US projects, we expect to see leading European manufacturers team up with US manufacturers such as Gulf Island and EEW tie-up from Massachusetts. Jackets are being fabricated from a wide European, Middle East, Southeast and East Asia yard base. As you can see from the pictures, a large amount of space is needed. We've seen in the US that Gulf Island produced the jackets for the Block Island offshore wind farm. Next, please. Larger turbines are driving larger wind farms with higher capacity factors and lower costs. We are seeing the current 12 megawatt GE actually uprated to 13 megawatts rolled out this year, next year, with a 220 meter rotor diameter, and the Siemens Gamesa unit at 14 gigawatts, which has already been selected for projects in Taiwan and the US. Next, please. The trend for larger and deeper turbines is presenting challenges for the installation fleet. Effectively, the new generation turbines cannot be installed by vessels that were built as close to 10 years ago. Next, please. And this creates opportunities for a wider range of vessels. Next, please. And larger and further from shore wind farms result in the use of DC transmission solutions with a jump in scale from AC to DC substations, something that will probably become a hotter topic in the US as, due to the far distance from shore of several offshore wind farms. Next, please. Accessing deep water, higher quality resources supports growth of floating offshore wind. And this is analysed in our upcoming offshore wind report. Floating farms are moving from demonstration to fully commercial farms in the second half of this decade, with up to $30 billion of capex expected. And we expect to see the first US commercial wind farm by the end of the decade, early next decade. Next, please. And this large approach calls for an industrial approach to building offshore wind farms to feed installation. Foundations, fabrication and assembly for a 500 megawatt commercial wind farm can see 125,000 tons of steel to 425,000 tons of concrete used, basis delivering one foundation per week. Next, please. And looking at the picture on the right, this is the latest, sorry, back one, please. Yep, that one. We can see from this picture on the right, this is the current project that's going in the water, the Kincardine project in Scotland. These semi-sub hulls will support 9.5 megawatt turbines. You can see just three there, how much area they require, how large they are. We have to upscale that on commercial projects to 25, 50, even 100 turbines. Next, please. Once the hull is produced, the turbine installation begins. On a 500 megawatt wind farm, we'd expect 30 to 40 floaters, basis 12 to 15 megawatt turbines. With 220 meter to 230 meter rotor diameters, this creates a storage challenge. As you can see from the photograph, these are quite sizable units. You cannot keep too many units at your quayside or in port. You need to start getting them into the offshore space and installing them as soon as possible. Next, please. With foundation installation phase, we have towing. So that's around 5,000 to 15,000 tons per floater at 2 to 3 knots. Pre-laying 3 to 9 mooring spreads per floater. That's 100 to 300 anchors and chains or synthetic ropes on a 500 megawatt farm, and hooking up the whole system. Next, please. And for all offshore wind projects, let's not forget the stable long-term operations and maintenance activity, around $95,000 per megawatt per year for a UK offshore wind farm. And this creates opportunities for onshore support, offshore crew transfer with nearshore crew transfer vessels, as we see on the left picture, and the further afield offshore service offshore vessels on the right, one of which is currently being built in the US under the Jones Act conditions. Next, please. So a word on wind to hydrogen, an enabler for offshore wind growth and global energy transition. Starting at the left of the slide, we see renewable energy sources such as solar and wind producing electricity. This in turn powers electrolyzers that split water into hydrogen and oxygen, the hydrogen going on to be used for power. building, heating, transportation, and industry. Just for information, around 10 gigawatts of capacity produces around 1 million tons of hydrogen per year. Currently, there's around 700 megawatts of hydrogen produced globally annually. So that would mean 700 gigawatts of offshore wind capacity. We don't see that happening. We see it being a split of onshore, offshore wind plus solar as part of the energy transition. Next, please. And the electrolyzers are seen onshore, offshore, and even turbine mounted. From the picture here, we see electrolyzers mounted, and for the Dolphin concept, this will be trialed on the Kincardine floating offshore wind farm in Scotland in 2 megawatt and 10 megawatt varieties. Next, please. So why is the US so interesting? Well, it's set to become a top 3 global player by the end of the decade. It has great potential in 5 zones: the North and South Atlantic, Pacific West Coast, Hawaii, the Great Lakes, and Gulf of Mexico, and a sustained pipeline to support the supply chain. Next, please. So US technical potential is over 10 times the current electricity consumption, and equates to around 2,100 gigawatts of installed capacity potential. So if we look at the gross technical potential for US offshore wind, that's around 46,000 terawatt hours. And that is 10 times the roughly 4,500 terawatt hours annual demand. And this will convert to around 13,500 gigawatts of installed capacity. Now that's gross potential. The graph on the right takes that gross potential and look at what is actually technically feasible to produce. And starting at the North Atlantic, we see around a 45% conversion factor, going around to the Pacific, which has the largest gross resource, converting at around 5%. But that in all will give around 2,100 gigawatts of installed capacity potential, a major capacity in the US. Next, please. So BOEM, which looks after federal waters, is currently reviewing construction operation plans and site assessment plans for around 14.5 gigawatts of projects in federal waters. This is the bulk of the US projects, although there are projects inland that fall outside BOEM's remit. Next, please. There is a clear pipeline set by East Coast state procurement targets, indicating 12 gigawatts of installed capacity by 2030 for $23 to $36 billion of capex. And this is underpinned by the 2035 targets for 29.1 gigawatts, which would amount to around $55 to $87 billion of capex for also, once installed, creating $2.7 billion of annual OPEX spend. And once these projects are approved, which we're expecting the first projects to be approved at the end of this year, early next year by BOEM, there'll be a large requirement for component manufacture, turbine installation capability, and onshore marshalling and support capacity. Next, please. So deep water potential in many states supports future floating offshore wind developments, especially in Maine, California, and Hawaii. The graph here shows the areas in blue will be water depths under 60 meters, basically bottom fixed, and above 60 meters is red. Some states like Hawaii, California, and Maine have a very high proportion of deep water over 60 meters. Next, please. So let's take away the opportunities and challenges for the US market. US is home to a technically exploitable offshore wind resource, over 10 times current electricity demand. The US has the second largest global wind installed capacity and can be a top 3 offshore wind player by 2030. Large amounts of, sorry, can you go back please on the third bullet? There are large amounts of capital required to meet state procurement targets, providing opportunities for investors, insurers, domestic manufacturers, and service providers, and port developments. Next, please. A recurring annual $2.7 billion of OPEX once the state procurement targets are met, supporting manufacturers, local supply chains, and offshore vessel operators. The deep water potential calling for offshore turbines will leverage the skills of the offshore oil and gas supply chain. Next, please. There are challenges such as competing demand for cheap gas and coal, which we see offset by lowering LCOE as capacity increases. Next, please. There's comparatively low level of investment and even strategic interest of US majors in offshore wind. This will be offset by the interest of the European majors and European utilities. There are challenges and opportunities to, sorry, please go back. There are challenges and opportunities to develop on and offshore grid transmission infrastructure, which is a whole new separate topic. Building local supply chains quickly enough to meet large project requirements while identifying sustainable pipeline of projects to maintain supply chain activities. We want to avoid a boom and bust situation, and balancing strong local content policy, including Jones Act requirements, could impact project economics that can be mitigated by partnerships with established players to create significant opportunities for US suppliers. Next, please. So thanks for listening. If you wish to learn more or see the report, you can go to www.worldenergyreports.com/wind, or contact me, Philip Lewis, at worldenergyreports.com, or contact Jim McCall at IMA@ASSOC@MSN.com. Thanks very much for your time, and I look forward to your questions.
Okay, well, thank you very much, Phil. Informative. Now I would like to welcome Fred Zaukman, the Head of Market Development and Government Affairs at Orsted Energy. Fred has nearly 30 years of experience in the energy field as an attorney and policy analyst. Welcome, Fred.
Thank you, Greg, and thanks to Marine Reporter and Offshore Engineering for including Orsted in today's event. We see huge value in these fora for bringing together U.S. energy sector, supply chain, and policymakers as we begin the transformational build out of offshore wind in the U.S. Next slide, please. For those of you not familiar with Orsted, just a brief history here. Orsted was formerly known as Dong Energy. That acronym stands for Danish Oil and Natural Gas. And as that name implies, the firm was heavily involved in fossil fuels. We operated combined heat and power stations in Denmark. We drilled for oil and gas in the North Sea. And we effectively operated as Denmark's investor-owned utility, distributing power and gas to end-use customers, primarily through oil, coal, and natural gas facilities, with only a few offshore and onshore wind farms in our portfolio. A growing societal focus on climate change, the launch of EU 2020 energy policies, and a growing consensus about the need to transform global energy systems led Orsted in 2008 to formulate a radical vision of transforming its business model from fossil fuels to green energy. Fast forward to 2017, we divested our upstream oil and gas business, and by that point, we were much more heavily invested in renewable resources. Today, where fossil fuels supplied 80% of our energy in 2009. By today, renewable energy accounts for 88% of our energy. And we anticipate achieving net zero energy generation and operations by 2025. The other trend that we've witnessed over time, and I'll get into this in a bit more detail shortly, is we've moved from our traditional footprint in the North and Baltic Seas and looked much more globally for opportunities. Next slide, please. So today, offshore wind is the fastest growing renewable energy technology in the world. And Orsted has nearly 30% of the global market share. We pioneered the technology back in 1991. By today's standards, the tiny Vindeby project off the coast of Denmark, 5 megawatt wind farm comprised of 11 individual turbines. Today, as Philip pointed out, any individual turbine is much larger than the combined capacity of the Vindeby farm. We've really had a strategic focus on driving down the cost of offshore wind, primarily through exploiting economies of scale and the technology, bigger individual turbines, bigger wind farms, standardizing installation and operation, and maturing the supply chain to achieve scale. And as Philip noted, costs of offshore wind have come down quite dramatically, so that in mature markets like Europe, we are already cost competitive with other renewable and conventional fossil generations, and we're quickly getting there in emerging markets like the US as well. Earlier this year, we commissioned the world's largest offshore wind farm at Hornsea in the UK. That's a 1,200 megawatt project. Just to give you some context, a single revolution of the turbine at Hornsea generates enough electricity to power the average British home for 24 hours. Next slide, please. So why the US? As I noted, back in 2015, as European markets were more maturing, we were looking for opportunities outside our traditional base. And the US market really bubbled to the top. And there are some really key market fundamentals. Looking at the left panel, just huge coastal electricity demand along the eastern seaboard of the US, major metropolitan region with load centers proximate to some of the key wind energy areas identified by the federal government. We also have a world-class wind resource in the Northeast, really comparable to anything we're seeing in Europe. And that's really important because for the significant capital investment we make in the turbines and other infrastructure balance of system, the greater the resource, the steadier and the stronger the wind blows, the more production we get out of our wind system. And that helps drive down the LCOE for wind. And finally, we have shallow water depths along the eastern seaboard. It's a large buildable continental shelf, which allows us to use fixed bottom conventional technology that we're accustomed to in Europe. Next slide, please. But I would say the fourth factor is really policy, and it's really the states' progressive policies along the eastern seaboard that's really driving the offshore wind market in the US today. Several states have stepped up, and today we're looking at a 25 plus gigawatt market by 2025. I'm sorry, by 2035. And that is really driving interest and investment. Orsted was really the first major offshore wind developer to enter the US market. But, we have significant company from major investor-owned utilities and other oil and gas developers looking to transfer their skill sets. Next slide, please. So we think we're really well positioned. We have a number of wind energy areas that have been competitively auctioned through BOEM. This real estate is strategically located proximate to the key markets I identified. We've been very successful in the first round of auctions conducted across the Northeast US. And as a result, we have at this point nearly 3 gigawatts of offtake with the states. The states ranging from Rhode Island, Connecticut, New York, New Jersey, Maryland, have all entrusted Orsted with the development of their first offshore wind farms. And we believe we have, just with our existing footprint, an additional roughly 7 gigawatts of development potential. Next slide. Just a word on our operational facilities. So the Block Island Wind Farm, of course, was the first offshore wind farm to be constructed in the US. This is off the coast of Block Island in Rhode Island. This project was constructed by more than 300 US workers. And with this project, we launched really a new American industry and really proved out that renewable energy through offshore wind is viable in the US. A number of Gulf Coast companies participated in the build out of the Block Island project, including Gulf Island Fabrication and Keystone Engineering. And this really demonstrated that there can be major investment for US companies and jobs for American workers, even in states without active projects. Next slide. Just a word on our coastal Virginia offshore wind project, which we developed as an EPC contractor to Dominion Energy. In June, we completed the installation of this 2-turbine pilot project. Our team and suppliers were able to construct the project even in the midst of COVID-19 and through hurricanes and other significant weather. And so we're really proud of what we accomplished here. The installation of these 2 turbines, these are the first to be permitted and constructed in US federal waters, really represents a huge milestone, not just for Orsted, but for the entire offshore wind industry in the US. Just this past week, the wind farm passed its reliability test and is now operational and ready to enter commercial service. And so we'll be transitioning into an O&M role on behalf of our client, Dominion Energy. Next slide, please. Obviously, to develop an entirely new heavy industry in the U.S. requires significant investment, and certainly a foundational element of this is in maturing the U.S. offshore market is improving and modernizing our ports and harbors for the deployment of offshore wind. Orsted is making a number of investments in various ports and harbor facilities really across the eastern seaboard. Whether it's for pre-assembly and loadout or construction, manufacturing and supply chain, longer-term O&M activities, really the need for redevelopment and modernization of our ports and harbors infrastructure is tremendous. And we've been actively engaged in public-private partnerships across our footprint to bring these necessary infrastructure investments to fruition, and with it, the significant job and economic development opportunities for our host communities. Next slide, please. I'd also want to briefly mention a recent announcement we made along with the shipbuilder Edison Schwest Offshore and our JV partner Eversource. So we announced earlier this month the execution of a long-term charter agreement for the provision of the first ever US flagged Jones Act compliant service operations vessel. This SOV will be engineered, constructed, and operated by ECHO as an integral part of the O&M of the Revolution, South Fork, and Sunrise offshore wind farms, the northeast cluster of our projects in the US. The vessel will be built at a combination of Edison Schwest shipyards in Florida, Mississippi, and Louisiana, creating well over 300 new construction jobs. The construction of this vessel will also have a broader economic impact on other US states hosting suppliers of major components, with some notable beneficiaries being North Carolina and Illinois for steel and main engines, respectively. While the offshore wind industry is relatively new to the US, states in the Gulf of Mexico who have long history in offshore-related industries stand to immediately gain from the high transferability of existing jobs over to offshore wind. Now, as I hope you can see from my presentation this morning, Orsted's quite bullish on the US offshore market. Now, that's not to say that standing up a new US-based heavy industry is without its challenges. In particular, I want to stress the importance of seeing progress at the federal level for the permitting of these projects. As you may know, the Department of Interior has put a hold on all permitting of offshore wind pending the completion of a cumulative impact study examining the economic and environmental effects of the expected build out of East Coast lease areas in response to state demand. No commercial scale wind farms have been permitted yet in the US. Now, this has caused over a year's delay, creating serious disruption to our procurement and construction schedules. BOEM is due to release the results of this study in mid-November, and we remain hopeful that this milestone will mark the resumption of the industry's forward progress. As excited as we are about the Echo vessel investment, we have a lot more activity in the pipeline that we're anxious to bring forward. Thank you for your attention this morning, and look forward to the Q&A later this morning.
Okay, Fred, thank you very much for your insights. Last but certainly not least, I would like to welcome Matthew Tremblay, Senior Vice President of Global Offshore Markets, ABS. Matthew holds the global responsibility for strategic planning and client development within the offshore market sector. Welcome, Matthew.
Thanks, Greg, and thanks to everybody for the opportunity to speak to you today. These were two very interesting presentations. I was very interested in everything I saw so far this morning. I'd like to spend a little time talking about the same subject from a slightly different angle and address some of the challenges in front of us in the offshore industry in the US. Next slide, please. At a high level, and in line with what you've already heard today from Fred and Phil, we're seeing several trends in new developments in the wind farm energy market in the US. We really are looking at trying to accelerate cost reductions globally, through the use of larger turbines with rated capacities of 10 megawatts and beyond. What we're going to see here and we see around the world is the demand for the wind farm support vessels is expected to increase significantly in order to support the planned construction projects for both fixed and floating offshore wind farms. And so the floating wind energy project pipeline is growing every day, with both fixed and multiple floating pilot projects advancing in real time right now. The emerging challenges associated with offshore wind farm development, as well as the supporting vessels, can really be categorized in the four groups. Firstly, the technical challenges to the design and complex installation many times. Second, the operational challenges of the industry and how are we going to continue to reduce the OpEx. Third, the environmental challenges, and that really does tie to the fleet of the vessels supporting this development, and how do we contribute to them having a lower carbon footprint as we move forward into the greener tomorrow. And lastly, regulatory challenges like that Fred just mentioned, and as well just in general to compliance with international and local regulations. Next slide, please. As we look at the US port infrastructure, we're all aware that offshore wind farms involve large components, including turbine blades and foundations, which have been increasing in size as the technology advances. Such components, they really require large areas for staging and assembly before installation at wind farm sites. So the transportation challenges of offshore wind, either moving these components long distances, which is over land very impractical. So given their size, it really does rely upon the ports and harbors along the East Coast and makes those very critical for meeting the developers, but as well as the state's offshore wind development goals. Key characteristics of an offshore wind port also include heavy lift capacity and the unimpeded access and load out for the specialized wind support vessels. Since 2017, 12 different port infrastructure investments have been announced for existing port improvements, redevelopment, and new hub development. The dimensions and characteristics of ports and the water depths of wind development areas provide some constraints and requirements for wind support vessels and designs. These turbine sizes are also necessary in sizing the installation vessels and the transport vessels that are going to be supporting them. Next slide. There are a number of new technologies supporting offshore wind expansion. And in looking at this, we can kind of drop them into three buckets of sustainability, technology solutions, and digital outcomes. Solutions like you see in the sustainability side here are really around the larger market and promoting the sustainability of the installation and maintenance of these fleets offshore. So the installation, for example, of hybrid power systems on the vessels installing and maintaining offshore wind. We've seen a lot of this recently, and we can expect to see more and more hybrid power systems being installed on vessels supporting the offshore wind market. Hybrid power systems really do promote an improved energy efficiency, but as well, we look at the use of LNG as a fuel, the use of battery storage on board for meeting peak loads, and overall the benefits of reducing emissions, both CO2 and NOx, but as well, optimizing engine loads, providing peak load power, and overall reducing operational costs through lower fuel consumption and lower maintenance. Beyond fuel-related technologies, the other solutions include smart functionality that incorporates sensor data into decision-making, as well as remote survey options to increase efficiencies and safety, with the goal of improving the operational performance and reducing the cost. And lastly, around digital, offshore wind farms are very capital intensive. The upfront investment cost makes up about 75% of the total lifetime cost of an offshore wind farm, which is quite high in comparison to other electricity generating technologies. The O&M costs break down generally around 11% operations, 7% life cycle management, 10% inspection, 12% preventative maintenance, and 35% corrective maintenance. So there's certainly room for improvement with these numbers through instrumentation, data collection, modeling through digital twin type of functionality, and analytics to move reliability centered maintenance strategies forward toward risk-based inspection, planning, and repair. Next slide, please. So where was ABS fit in here? Class has had a role in some manner or another since the start of the offshore industry. The role of classification can be looked at through a number of ways, but the ways that we've been participating traditionally, and we still see ourselves participating in the development of offshore wind, is firstly through the development of rules and standards to promote the safety of the workers, the property, and the environment. Providing design approval in accordance with both class and industry standards, performing surveys during construction, ensuring that the construction is in accordance with the design and the approved standards applicable to the project, as well as surveys during installation and after installation to maintain that the floating asset or fixed asset is in the condition that we expect it to be. Specific to floating wind, though, this is even more applicable. When you look at ABS, there we go, one more. Next slide, please. Thanks. ABS really has positioned itself as many other classes as the trusted advisor and as a third party involved in the floating wind market for more than 10 years, with experience on more than 10 different types of design concepts and 80 megawatts of installed projects. Those projects today include 3 8.4 megawatt units offshore of Portugal and 5 9.5 megawatt units that'll be offshore of Scotland. ABS has been providing class support during the global energy transition and through the development of these projects offshore. And we've provided the class service and the independent verification necessary to ensure that the assets themselves are able to perform as expected and doing so in a safe and efficient manner. Next slide, please. Looking specifically at some of the rules and standards and activities that ABS has been involved in, ABS approaches offshore wind very similar to what we've done with the rest of the offshore industry for the last 70 years. focusing primarily on the floating structure with its mooring and marine systems, and applying the same principles to bottom-founded installations as well. For the turbine itself, right now in floating wind, the trend is to use the same series of turbines currently used in bottom-fixed offshore wind developments. And we don't foresee there being any unique requirements for the turbine itself, and expect to continue to rely on IEC type certification scheme that's proven to be successful over the last decade. But going back to the floater, the main difference from a traditional production platform that you would have offshore for hydrocarbon production is the loads. Back one slide, please. Yep, is the loads. Because the actual physical loads on the asset itself, the floating asset, is now horizontal instead of vertical. And so as engineers, how we go about analyzing these loads has to change. And to support this, ABS has developed guidance notes on global performance analysis for floating offshore wind turbines. As well, there are additional guides that are available. And ABS actually sits on the IEC TC88 panel that has been convened to standardize the global design requirements for floating offshore wind turbines. Next slide, please. So ABS offers a roadmap supporting the projects from concept, basic design, and detailed design through construction and operations. Due to the ever-increasing environmental regulations, owners of wind farm support vessels may consider adoption of green technologies such as hybrid electric power and alternative fuel sources to reduce emissions and innovate along a low carbon footprint. But regardless of the vessel's design or its fuel, ABS can provide classification services for a wide range of wind farm vessels and the wind farms themselves. But our goal at ABS is to support the industry's adoption of new technologies, making offshore operations safer and more efficient. Next slide. I'd like to just end with referencing 3 different projects, specifically, one of which was mentioned today, and just touch on a few highlights to give you an example of some of the activity that's occurred over the last few years. We heard about the Block Island wind farm that Fred mentioned a little earlier, and just to kind of frame the installation of these this wind farm, I'd like to share a little bit about some of the vessels that worked on this project. The Weeks Marine Jones Act vessels, the Weeks 533 and 526, were used to install the jacket foundations offshore. The Seacor Marine Jones Act lift boat LB Robert assisted with the foundation installation and was used for piling and lifting the platform. Fred Olson's wind carrier foreign flag jack-up vessel, the Brave Tern, was actually the vessel used to install the 5 wind turbines. So that's the one foreign flag vessel that we're going to talk about here. But as well, as due to the Jones Act, the Seacor Marine liftboat Paul and liftboat Caitlin were used to deliver the wind turbine tower components, including the blades, nacelles, and tower sections to the wind farm project site. And lastly, Atlantic Wind Transfers is the first US-built crew transfer vessel that the Atlantic Pioneer, and has a 20-year contract to provide transfer and service of personnel to the site. So in total, we're counting 6 different Jones Act vessels that were utilized installing this one project offshore. Second is the VARD 407 SOV. ABS has granted the first approval in principle to VARD for its design of a Jones Act service operations vessel. And the AIP was awarded at the Workboat Show in 2019, where VARD has developed a customized version of their 407 design for a US variant, compliant with the requirements in the United States for a US flag vessel. And lastly, the WindFloat Atlantic project, as well, was already mentioned. The WindFloat Atlantic project was followed through and installed in 2019, being the largest turbines ever on floating foundations, with a total generating capacity of 25 megawatts. There were actually 2 projects operating in parallel, the WindFloat Pacific in Coos Bay, Oregon, and the WindFloat Atlantic in Portugal. The Oregon project did not go through, but the lessons learned from that project will benefit future floating offshore wind development in the US. As part of that project, ABS hosted and facilitated a workshop with all the regulators that may have jurisdiction on a floating offshore wind facility in the US continental shelf: DOE, DOI, BOEM, BSEE, USCG, and whatever other alphabet soup letters we can come up with. But all of these government agencies were part of this workshop, determining who is going to be focused on what aspects of the project. So lastly, I just want to mention that the University of Maine development that we believe will be the first commercial scaled floating offshore wind turbine in the US waters. ABS has also been involved with that project from its start, and 100% of that preliminary design review has been completed. So next slide. I'd like to close this out, just thanking everybody for the time today. ABS is available, and myself as well, specifically to answer any questions anybody may have and support the market moving forward as the experts in the US on the offshore wind regulatory regimes and the projects that are going to be required to support the development offshore. Thanks, Greg.
Well, thank you very much, Matt. That concludes the presentation portion of the program. And now I would like the presenters to switch their cameras on for the Q&A. There's actually quite a few questions that have come in. We're going to try our best to whip through them in the next 15 to 20 minutes. The first question is targeted to Orsted. And but Matt, this might be one for you as well. And hold on, there's more questions coming in. Apologies. Okay. When do you foresee the low carbon technologies to become firm requirements in the future vessel tenders as opposed to optional as we see in current vessel tenders?
Requirements, I don't know that I see it happening in the near future. For the vessels that would be supporting the offshore wind, primarily installation and maintenance, the EEDI, EEXI type of requirements that are international standards for emissions wouldn't really apply the same way that they would do for a blue water ocean going vessel. So, if we do see requirements being put forward on emissions, I really don't expect it to be something that within the very near future, that is from a statutory perspective. What we are seeing, though, is the financing behind a lot of these projects making those requirements. So while it may not be a statutory requirement, we're seeing requirements from companies like Equinor, Shell, and some of the major banks that are doing the investments to behind some of the field development, starting to put requirements around sustainability, continuous improvement around emissions as part of the financial aspects of or requirements behind some of these projects.
Fred, would you like to weigh in on that?
No, I really don't have anything to add. I think that's a pretty robust response.
That's perfect. Just as a start as well, we got many questions regarding the availability of presentations after. The webinar is being recorded and it will be made available to everyone who attended afterwards. So that's good. So I know we covered it in many of the presentations, but when you look at the major controlling factors on development, Fred, to start with you, if that's okay, or pass the buck, but what do you see today in a bullet point type scenario? What do you see as the major controlling factors on future development?
Sure. So obviously, again, the demand is being fueled by the states and really motivated by desire to meet pretty aggressive greenhouse gas reduction targets, renewable energy targets, and frankly, economic development and jobs. I would say that, constraints, are mainly, as I mentioned, around permitting. We really do need to see a more rational and streamlined permitting regime to provide more certainty and predictability around our timelines. We are working quite closely with organized labor around workforce development so that, when we are ready to put steel in the water, the trades are skilled up to the point where they have the necessary proficiencies and skills. And then, the third factor is the infrastructure investment. And as I've mentioned, we really see a diversity of needs. I thought, Matthew did a great job of highlighting, how various ports along the eastern seaboard can accommodate different usage within the offshore wind space. whether it's for marshaling or for O&M, and that will require a significant public-private investment to make sure those ports and harbors are fit for purpose for the need. So those are some of the key items, I'd say.
Greg, if I could expand on that just a little bit as well, the one other aspect of that on the logistics infrastructure piece that Fred mentioned is the availability of the somewhat customized vessels to support the market as well. There is an opportunity to retrofit some existing vessels for some of the services that are required offshore. But if you look at the goals of installed capacity that each of the states have, the vessels to support that level and quantity of installation, they don't exist in the U.S. market right now. And we would have, from my perspective, had to start building about 30 months ago to have the vessels that are at least the U.S. flagged vessels, Jones Act vessels, to support that capacity of installation offshore. So that really is a key piece, and that when you look at the dry dock space in the U.S., a lot of it's taken up by U.S. government shipbuilding, and a lot of the other parts of it are utilized or not prepared to develop these type of vessels. So construction capacity to make sure that we've got the vessels available to install and transport these turbines is another big piece of that as well.
And just to add to that, I think if you look globally, obviously we're looking at the US taking off in quite a substantial manner over the next few years. So one of the solutions, for instance, as we've seen with Block Island and Virginia, was using foreign flag wind turbine installation vessels to support those projects. And two challenges coming up in the future. One is the rest of the world's going quite strong on offshore wind as well, particularly Europe and Asia. That's going to soak up a lot of that installation capacity. Secondly, as the turbines get bigger, and for some of these large US projects, you are looking at the larger turbines being used. That actually begins to limit the number of wind turbine installation vessels that are actually available to do the work. And then third, when you're looking at a gigawatt project or around a gigawatt project, depending on your weather windows and your construction schedules, you might even need to use a second wind turbine installation vessel, as has been seen on various North Sea projects and some North European projects. So there are some supply chain issues there, and it's not just simply a question of building lots of US tonnage for wind turbine installation, because you need the pipeline to support that and make sure that the owners who invest in that and are investing on 25-year basis of lifetime can actually pay back their investments and make their money. So there's quite a lot of different things in play to look at. It's going to be a challenge for those asset owners.
Okay, thank you very much, Phil. No, thank you, everyone. I'm going to combine a couple questions here because we have a lot of similar questions, but the next one is going to be targeted to floating wind. It was targeted to Orsted, and it specifically was asking, what is the appetite to Orsted to look at the West Coast? And obviously you're involved with some fixed bottom applications. What is your take on floating? But I'll expand that question a little bit. We talk a lot about the fixed versus floating. What's the future? So I'll ask Fred if you can weigh in on the Pacific piece of the puzzle first, but then Phil and Matt, if you can just kind of discuss the way in which you see the floating systems going.
Sure. So yeah, great question. California is really, I think, one of the prime markets that has not yet embraced offshore wind as a specific target, although it's clear that in order to meet the state's ambitious greenhouse gas reduction targets, offshore wind has to be part of the mix, and that in the Pacific is effectively a floating technology. So we are actively involved in discussions around market development in California. There are some challenges to overcome. It's a heavily conflicted part of the world with military defense usage in particular, strong environmental concerns. But we do think that a market there is inevitable, and it will be a significant market, upwards of 10 gigawatts to start. You know, we're really focused in the short term on our opportunities for fixed bottom development. We do see a future for floating. We see and are monitoring the innovations that are coming down the pike, and we do see a crossover point where floating will become cost effective relative to fixed bottom technology, and so, you know, it's not in our immediate plans, but certainly in the medium and longer term, it's a technology that we're very mindful of.
Yeah, so as a technology, you know, ABS has been very involved in floating wind. We've approved between 10 and 12 different designs of offshore floating wind. We've classed the first commercial offshore floating wind projects that have been installed around the world. And you know, the one thing I want to highlight maybe around floating wind is that the regulatory regime may be a little bit different. The maintenance is definitely a little bit different for a floating structure as opposed to a fixed structure. And the manner in which you have to go about thinking about the project economics then change. But as well, it changes the infrastructure requirements as well. You're no longer, you know, taking piles offshore or jackets offshore. You're now floating out assets out from wherever they've been built. You know, is it going to be efficient to build these in the U.S. or maybe build them in Asia and transport them to the Americas? You know, these are all different challenges around floating wind that really do get affected by the geography and the infrastructure available, as well as the differences in regulation and maintenance schemes around floating wind. So from there, I think Phil's probably got some good insight as well.
Yeah, no, thanks, Matt. I think that there are certain analogies to the history of oil and gas here. You start near shore, lower cost, easier to install projects, but you know, nobody really wants these wind farms sitting off their back garden or you know, off their nice beach when they're on holiday. They want them offshore, further offshore. Now, the continental shelf goes quite far in shallow water where you can build out to that. But also on the East Coast, I mean, but there are places on the East Coast where it does get deep and where they're close to those, relatively close to demand centers as well, where you could see the need for floating offshore wind. On the West Coast, it gets deep very quickly, and where their demand centers that want to go green, they're going to probably require floating offshore wind. Hawaii as well would need floating offshore wind. But one of the real advantages with floating offshore, and I think as we go forward, we won't talk about fixed and floating per se. I mean, floating will become mainstream, and it will become mainstream quite quickly, quite simply because it allows for bigger turbines, much bigger turbines than for the bottom fixed. So putting those offshore, larger turbines getting much better capacity factors, generating more capacity for your dollar, basically. Getting that back to shore, that's in its own sense, using the larger turbines will bring down the cost of the floating offshore turbines, and that starts to create a virtuous circle where the cost keeps reducing and it gets more cost competitive. It doesn't mean the end of fixed offshore. There's certainly going to be plenty of fixed offshore, and there's going to be plenty of floating offshore, but the better quality wind resources, lower cost, eventually will come from the floating offshore.
Excellent. Thank you all. I know we're kind of getting into our time. If you guys don't mind, I have we have a lot more questions. And for everybody watching, the questions will be presented to each of the panelists and they will get back to you, or we will answer them in some way, shape, or form. But I have two more questions if everybody has a little time. First and foremost, obviously, the talk around the cost of the energy is always an important discussion. What do you see? Where do you see the biggest opportunity to improve the cost of the energy delivered? And again, that's for anyone.
One of the big areas I think we just touched on in that last point is on the turbines themselves. Um, as they get bigger, their capacity factors increase. As the capacity factors increase, the levelized cost of energy on projects begins to come down. There are different areas in fixed and floating where cost efficiencies can be made at all levels. For instance, floating at the moment is very much in its infancy. Yes, it's getting to the pre-commercial stages, but there are major savings to be made in the mooring spreads, to bring down the weights going from chains to synthetic fibers, in the actual foundation structures themselves and the turbines. Whereas in the fixed bottom fixed units, that's quite a mature industry already, and there's a lot of economies of scale and economies of scope being driven into that. That's not to say savings are still going to come, but it's a much more mature industry. So it's not a one answer fits all.
Yeah,
Yeah,
to Phil's point,
Oh, go ahead. Yeah, please.
just to reinforce Phil's point on the turbines and what I mentioned in my presentation is, 75% of the cost of a field development is that upfront hardware and installation cost. So while there's always opportunity to promote savings on the back end, on maintenance, et cetera, through the use of improved maintenance systems, risk-based inspection, digital twin technologies to really start forecasting any maintenance issues, I would agree that looking at the front end startup costs is where you're going to get the most bang for the buck.
Yeah, and I would agree as well. I don't think we've seen yet the full exploitation of economies of scale and turbine technology, and that will continue to drive the levelized cost of energy down. I think it's also going to come from just the maturation of the U.S. market. The Block Island Wind Farm, that was largely bespoke because we effectively had no supply chain, no logistics, no fit for purpose installation vessel, Jones Act compliant here in the US. So as that supply chain builds out, I think we will see greater and greater efficiencies as well.
Okay, thank you guys. One more question, and it would not be a U.S. maritime discussion or an offshore discussion if we didn't bring up the Jones Act. Matt, I remember last year in New Orleans, ABS held an awesome presentation when we were all together personally regarding the breadth of offshore wind and its impact on the U.S. maritime port and logistics sector. So when you look today at the viability and the need for Jones Act compliant offshore installation vessels, but I'll just open this up to every type of vessel, do we have the capability to feed the beast, as it would say? Do we have the capability to keep up with the demand?
I think we have the capability, definitely. I mean, I think the position that overall that the industry and that the regulators have settled on is not going to change, in that, if you're transporting from the shore to the offshore continental shelf, that's required to be a Jones Act vessel. The vessels doing the installations themselves, provided they don't come to shore and provided they're not bringing any equipment offshore, those are not going to be required to be Jones Act vessels. And I don't foresee that changing, and I don't foresee the Jones Act itself changing in the near future. That's not a regulation that I see the politicians grabbing onto as something they really want to plant their flag around at a national political level. So I think the real question in front of us is, can we have available to the market the U.S. Jones Act vessels that it's going to need to support the installation goals that we have offshore?
I'll just add something to that point. There are a backlog of projects sitting with BOEM for approval at the moment, as has been discussed earlier. Vineyard being the major case that's being looked at, that once that's approved, in theory, that should lead to the approval of quite a lot of other projects quite quickly, bringing on quite a lot of potential construction requirement for a lot of capacity. Now, we're talking of this 12 gigawatts by the end of 2030 as state procurement targets, 29 gigawatts by 2035, so 10 to 15 years. The European market has sort of took nearly 30 years to get to sort of 18, 90, well, 20 gigawatts, let's say. The US is going to do that in a significantly shorter period. So it's got to develop those supply chains, those vessels, that equipment in a much shorter period. A bit of a boom in one sense, but then what they really got to look at the back end is that it doesn't go bust, that the pipeline still remains there, that leases keep coming through, federal state procurement targets keep coming through for more and more projects. So these vessels and equipment keeps getting used. For the operations and maintenance vessels, that shouldn't be such an issue, because if they're on 20-year contract, 25-year contracts to support the wind farm, there should be use for them. But it's more for the construction vessels where you want to avoid the boom and the bust.
Fred, would you like to add to that?
No, I mean, I think that is all well said. I mean, we're very supportive of the construction of U.S. flag vessels for all manner of installation and operation. I think, we're looking at it more from the standpoint of, what can policymakers do to incentivize that construction, rather than putting mandates on the industry, which we think, at least in the short term, because of the supply-demand balance, could create some unintended consequences and constraints.
Okay. Well, gentlemen, I want to thank you for your time. I want to thank everyone who attended as well. Again, I think it was a very successful webinar, and again, have a great day.
Thank you.
Thanks, Greg. Thanks, everybody.
Thanks, Greg. Thanks all.